Okay, our next chapter is on probability. So today we will discuss about the property on addition for probability. So what is probability? Probability is all about chance, the prediction, the uh, how likely something is going to happen. So that is actually probability. If you something has a low probability, that means something has very unusual chances or unusual occurrence it can happen. So if you look at your daily life, we often see probability in our daily routine. For instance, this morning I checked the weather, that what is the weather of Lansing. So I checked, okay, there is a chance of 40% that it could be rain. So how likely I should trust on this prediction that it can be a rain? Or if we look for forecasting, like stock market, you see forecasting. So how, and somehow you see predicted what will be the dollar value in another currencies. So by this year, the currency will rate will go up or will go down. What will be our economy? So these are all predictions we make in our daily life. Another example, if you go to the doctor, and sometimes doctors say, if your mother has diabetes, it highly likely you can also have diabetes. These that how he tells you the percentage of having a diabetes to you if your any of your grandparents or parents has diabetes. Or sometimes a person unfortunately is suffering through cancer from cancer, and a doctor says, okay, there will be a limit of his life, or like he will be living 3 years more, or cannot. So how likely it can happen, or how do they predict, how do we believe it? And sometimes you see the flights, they overbook their seats. Sometimes they book for 400 passengers, but though actually they have seats of 300 in the flight. But how do they predict these things, that 100 people will not going to be in the flight and they overbook their tickets? So this is all happening because of probability. So probability is everywhere. Even during COVID-19, we are um, uh, suffering through this problem. So it's pandemic situation, so everyone is having a tough time through it. So how we predict, okay, if we are getting vaccinations and if we are using precautions, then how can we can overcome this situation? How likely that by the end of 2021 COVID-19 will be gone, so everything will be normal? So this is our daily life prediction. We use it in our daily life. So this is probability most often used for forecasting, predicting something for our favorable outcomes, for our favorable choices, that we want this to be happen. So how likely it can happen, what are the circumstances it can have, and how likely we should believe on it. So this is why we use probability in our daily life. So there are some key things that I will discuss first. Keywords are there that I want you to know. For instance, what is event? For getting any chance something is going to happen or not, you need to have some, first of all, some experiments. So experiments is what you are doing. So that is what we call procedure. In statistics, we call it procedure. So procedure is what you are doing or what is happening around you. So that is called procedure. So event is the collection of outcomes of a procedure, or it consists of a subset of a sample space. So event is basically what you are looking for. What are the favorable outcomes you want to have? For instance, if I say, I want to go for shopping today, and so favorable outcome, let's say I am going to buy a t-shirt. So okay, so my favorable outcome is that I want to buy a t-shirt of red color. So this is an event. So this event can happen. What is the procedure? Going to the market. And simple event is event with a single outcome is a simple event. For instance, if I'm going to the market and there I have seen lot of shirts, lot of red shirts, lot of t-shirts are there. So each shirt is a simple event in that. So sample space is the collection of all simple events or all possible outcomes. So there are a number of outcomes you will see. There are a lot of things in the market and you want to choose from them, from it. So that is our sample space. So event is the collection of outcomes of a procedure or the favorable outcomes you want. Simple event is a single outcome, is called event with a single outcome is called a simple event. And sample space is the collection of all simple events or all possible outcomes. These are our sample space. I am going to discuss it in a few seconds with some examples. For example, we are tossing a coin. So a coin has two things. One has head, another is tail, right? You are tossing it one time. So what is the procedure? Procedure is tossing a coin. And I want to get a head from it. For instance, if you have seen, like sometimes we everyone I think have seen cricket. So sometimes it's hard to decide who will be going for batting first and who will be going for bowling first, so they toss a coin. So favorable outcome, let's say I'm on the team of head side. So if I want my favorable outcome is head, so if head it will come, then I will go for a batting first. So my favorable outcome is like event is here, head is my event. And sample space, what can be the outcomes you can have if you flip a coin, what kind of things you can get. So that is my, either you can get head or you can get tail. So that is my sample space. You are getting that event from a sample space. So for instance, you are flipping, and similarly you are flipping a coin three times. I get first coin, second coin, and third coin. So I don't know what kind of outcomes I can have, but I have some possibilities from where I can get something. And I want to get head, tail from this outcome. Like I want to get first head and then tail and tail, or two, or I just say that I want to get two tails and one head. So what could be the favorable, what could be all possible outcomes from it? The possible outcomes you can have, maybe on the first toss, you get first time head, second time you flip, you get tail, third time you flip, you get tail. So your one simple event is head, tail, tail. Another simple event or another possible outcome you can have, what is that? Um, you can get head, tail, second time, let's say you get tail, and third time you get head. So third time you might have head first time, second time head, and third time tail. Similar, or you can have all tail, head, or you can get all tail, or you can have there could be a possibility of getting a tail first, then head, and then tail. So this is how we see all possibilities in this. So the possibilities, first I write it down that how many possibilities I can have. Here I have 8 number of possibilities that it can happen from our experiments. So these kind of outcomes I can have. But the event is my favorable outcome. I want to get two tail and one head. So this is existing in this set in our my sample space. So this is how I am telling you what is the procedure, what is an event, what is the simple event, and what is a sample space. So simple event is, if you define a simple event, so simple event means these are the ways that can help you to accomplish your events. Like I want to get two tails and one head, right? So for instance, in these sample space, how many of these have two tail and one head? This is one simple event that can accomplish my event. So one head and two tail is in this one. So this is the second simple event that can help me to get my event. So two tail and one head in, and where? So this is also the third one, and no other I can see which has two tails and one head. So these are all the simple events. So these are the ways that can accomplish my all events. So this is how I'm defining the simple event, sample space, all possible outcomes, and event is the favorable outcome that you want, and procedure is the experiment you are doing. Hope it makes sense now. Second example, most often we will see in the entire course for the probability. is rolling a die. So you have seen a die has six faces: one, two, three, four, five, and six. And all of these are independent, and all of these faces are equally likely to happen. So for instance, I'm going to do experiment. I'm rolling a die one time. So this is my procedure. I'm rolling it one time. So what I want to get, let's say I want to get three. And from it, so that is my favorable outcome. This is my event. So sample space is all possible outcomes. You can get one, you can get two, you can get three, four, five, and six. So these are all of my outcomes that I can get from it. So this is how I'm defining. This is my sample space and event and the procedure. So if I look for the simple event, the ways I can get from the sample space in the event, so that is only one simple event. Here is only one existing in it. So next is probability. Again, come to the definition of probability. What is probability? Probability is all about a chance something is likely to happen. What are the chances it can happen? How likely this is going to occur, or this is going to happen. So probability you define is a chance that whether it's going to happen, whether today it's going to be a rain or not, whether I'm going to go for a shopping or not. So these are all kind of chances that I'm going to decide in our daily life. So probability is there. If you write mathematically form, that how you symbolize it or see it in mathematics or statistics. So probability is defined by the letter P. And if you define event, what is the favorable outcome you want to get? So that is represented by also all the capital letters of A, B, and C. And D, you can define it like that. Or if you are writing it down, P parenthesis A, so it means P of A, probability of an event A that is happening. And you are writing it with P of A throughout of this chapter. So now again come to the types of probability. What types of probability you can get? Well, if you are tossing a coin or rolling a die, or you are drawing a cards, which will be a deck of card, I will be showing you in a minute. So uh, this is not that helpful for us to getting some to predict something in our daily life. The most important thing for us, that how we can categorize this probability in our daily life, how what kind of probabilities I can have and how we can define it. So one type of probability is, you will see in very common, that is the exact definition of probability, that what it is. That is called classical probability. Classical probability means probability that is based on a chance of your favorable outcome of your event that is occurring. And each simple event must have an equal chance of occurring. So what does it mean? It means you hasn't done any kind of experiment. You are just saying, okay, I will roll a die. It has six sides, and all of sides have equal chance of happening. And you can either get one, two, or three, or four, or five, or six. Anything, all of these faces have equal chances of things can happen. Like, do you remember if I once I discussed about randomly selected procedure. So that was also um, equally equal chance of occurring things, like randomly selected. So all of the things have equal chance of selecting. So being selected. So this is how you define the classical probability, that you haven't done anything, but if you want to choose something from your random sample or your experiment, then all of the events have equal chance of happening. So that is called classical probability. Just rolling a die, the example is tossing a coin or drawing a card. So this is so it means it hasn't happened, but you are thinking about it, what could be the probability. So if you're finding a probability of an event A, It could be anything, procedure, anything. Event is your favorable outcome. So the number of favorable outcome that could occur from an experiment, so could occur, not has occurred or has happened. It could occur and divided by the number of simple events that is in your sample space. So that is called probability of an event A. And this is what we defined by classical probability that we are going to use very often when we don't do anything and we just predict something. If this happen, then this can happen. The probability of this thing, it would be this one. So this is the exact definition of probability. So this is one type of probability that is called classical probability. So uh, if you are predict something on your experiments, like you have done something, so three types of probability. One is you didn't do anything and you are thinking if this happened, then this can happen. So that is classical probability. Objective probability, or in terms of objective probability, we are defining observed probability, or it can also be called empirical probability. Empirical probability or observed probability, these are the probabilities that is estimated based on your observations. Like for instance, COVID-19. What is your you want to get control on your COVID-19? Like what is the chance of that COVID-19 could be controlled by the end of 2021? So that is my probability of chance of happening. What I want it to be happen, I want to overcome the situation of COVID-19. And um, what is my experiment? That I am doing vaccinations of people, and I have, for instance, I am giving thousands of people, if of or like millions of people, if I am uh, giving them vaccination, then the outcome is that they are not being affected by COVID-19, and it is the graph is becoming low and people are being less affected by COVID-19. So that is my experiment. I analyze this. I have given them a vaccination, and then I saw those results, that look the results, that whether it's being controlled or not. So, and then I'm going to predict something for the future. So this means something you have done an experiment, and you are going to observe something from that experiment. So that there we will use empirical probability, that you are predict something based on your experiments that you have done. So that is called observed probability or empirical probability. So this is how we can say observe. This is our objective probability, empirical probability, or observed probability. This is second type of. So third type of probability is subjected probability. Subjected probability that you can guess, educated guess. So what does it mean? Where do we use it? For instance, sometimes the companies use it for their favorable things. Like for instance, if like Apple, before launching an iPad, they did not know anything whether this item will be successful in the market or not. They whether people will be going to use it, or they will get the profit from this by launching this product into the market. So they did not know anything. They just make a guess. So those guesses were made by using subjective probability. So that is your subjective probability, that you make a proper guess on it. Like for instance, they may make some kind of features in that iPad. They may make some kind of applications in there that people will be more interested in. It's very handy. People can take with them anywhere through traveling or something. So people will use it. So anything that can help you to um, that can help you to predict something, that can help you for the successful outcome for the future. But you don't have data, you have not done anything, and you don't have any experiments. You are just making a guess that it can happen. So that is called subjective probability. So this is how we define the three types of probability. Very important for you to know. One thing is that should happen. That is called classical probability. You haven't done anything, but you are guessing based on what could be the outcomes and what should happen. So that is called classical probability. So this is should happen. And if you define empirical probability, so that means it has happened, or you did it, you performed something, you did it, performed something. And subjective probability is just an educated guess. So let me give you some of the examples that I can also ask you to know that whether it's empirical probability or it's classical probability, what kind of probability it has. So let me give you a few examples. This is one of the examples for classical probability. One is, so classical probability, make sure it should happen. You haven't done anything. So probability of rolling a die or rolling a one when a single die is rolled. So the procedure is here that you are rolling a die. And event is that what is the probability of getting one from it? So this is probability of one. What is the probability? And when you uh, when you roll it for single time, what is your sample space? What is the total number of items that you can get from it? So if you roll a die, make sure there are six possibilities from it. So you want to get one, and one occurs in your sample space. Let me show you. Where is that? Yeah, this one. So we are looking for probability of one, but one occur only one time in these spaces, and we are not getting anywhere. So the total number of sample space is six, and one occur in it only one time. So it means it is, and all of these numbers have equally likely to happen. So number of times one exists in our sample space, that is one, divided by number of all possible outcomes, that is six. So this is the probability of getting a one. So this is classical probability. You did not do anything, and you know that how many times number one occurred in your sample space. So that is called that one time it occurs, and divide by total number of outcomes, which is six. So this is giving you the classical probability. The next thing is a deck of cards. If you don't know deck of cards, I have some to show you. So these are the deck of cards. So these are the deck of cards. Like this is club. This symbol is club sign. And this is spade sign. So this is, I'm choosing 9 in there, spade. And this is spade. And this one is diamond sign. And if you haven't seen, diamond, and one has to be hard. Where is hard? One second. So this sign is hard. This sign is of hard. So in this cards, if you see the total number of cards I can have, the total number of deck of cards are 58, sorry, 52 number of cards you can have in a deck of cards. So total number of cards, total cards are 52. And how many number of, and all of these, each of these card signs have their numbers 2 to 10, and the 3 are jack, king, queen, and 1 is ace. So ace look like this. This is ace. So, and jack, king, queen, it can have. So each of these are 13 spades, 13 club, and 13 diamond, and 13 hearts I'm having. So total is 52. My question is here that the probability of selecting a heart from a deck of cards. What is the probability of selecting a heart from a deck of cards? So it means one thing you need to know, what is the procedure? Procedure is you are drawing a card, and I don't know which card I'm going to get, but I'm drawing a card. This is the procedure. So what you want to get, so that is your event, the probability of selecting heart. What is the probability that if you select any random from this, what is the probability that I am going to select I'm going to select heart. What is the probability? So, but the number of hearts, it didn't say anything that one heart, two heart, jack heart, queen heart, which one? It didn't say anything. This is just heart. So total number of heart cards, we are having 13. So total and the number of favorable outcomes are 13 because total heart events in 52 cards are 13, and divided by the total number of cards, all number of sample spaces, like all number of simple events you can, all number of outcomes you can get. So total, if you count all of these cards, so these are 52, right? Now you have to count the percentage, like the portion. So probability is giving you the portion. So let me find it out. So if you divide 13 divided by 52, so this is giving you 0.25. So it means 1/4 portion of all the cards is giving you hard card, because here you have seen the hard card, we have 13 all in there, and it is making 4 sections, dividing all these cards are dividing your sample space into 4 sections. So it means so this is giving you, it means 25% chance that you can get hard from the deck of cards. So this is how we define the classical probability. So the next thing is observed probability or empirical probability. So this is kind of objective probability that is based on some experiments. So the first definition is, first example I am having, flipping a coin, and flipping a coin 100 times. Flip a coin 100 times, it means something has happened, right? So it did it. So flip a coin 100 times. So this is my procedure. Procedure is flipping a coin 100 times. You have got 64 tails. So that means the outcome you get is 64 tails. The total number of times you flip the coin is 100. So what is the probability of getting tail? You have done an experiment and you got 64 number of tails from it, like number of events that occurred, number of 64 tail has occurred from 100 number of tossing a coin. So the sample space is, total number of outcomes is 100. So 64 divided by 100 is giving you 0.64. It means 64% chance that you are getting, that you got, and because this is observed probability, 64% you got uh, tails in this experiment. The next is Alice completed 385 out of, it's not if, of first 528 passes. Find the probability that Alice will complete a pass. Like this is, he was in a game and he make passes 385. Total passes he was having 528, and from those passes he scored 385 passes. So what, find the probability that Alice will complete a pass. It means something has happened. This is the experiment that he made the passes, and he, we are going to find the probability of completing a pass. Then if you are going to find the probability of completing a pass, then how many times he got passes? 385 times he got passes, he completed those passes. So what are the total number of passes he was having? 528. So this is giving you the probability of completing a pass. So if you calculate it, so this will be giving you, so this is in 3 decimal places I'm going to write because I need to find the percentage, 0.729. So it means 72.9% the probability is that he completed the passes. So this is the uh, example of observed probability. The next example is, now I'm going to ask you, uh, this is a random deck of cards. What is the probability of selecting a 2? This 2. But he hasn't mentioned this 2 is what? This is for spade. But he didn't tell you anything. This is spade card, heart card, diamond card or club card. He didn't tell you anything. So you need to know, but this is asking you selecting, find the probability of selecting a two. Now I want you to take a pause on this video and think about it. What is the procedure? Which probability it is? Is it classical probability or is it observed probability? Or you need to find out what is an event, what is your favorable outcome from it, and find the probability for that outcome. So I'm holding it for for 5 seconds, and then we will come to it later. Okay, so the the experiment is, you need to know whether there is some experiment he made it. He didn't do anything. He didn't say that he draw a card and then he found the number of twos in there. No, he didn't say anything. He just said, we have a random deck of cards. What is the probability of selecting a two? So the two we are having four, four signs of club cards we are having. So in each four of those cards, like heart, spade, club, and the other diamonds, you got each of those cards has two in that, in each of them. So it means, so total number of two, how many in the cards? So which is 4. So the number of 2 I am having is 4, right? So the total number of outcomes, like total number of cards, is 52. So procedure is, you are drawing a card, and event is you want to get 2 in that, probability of getting card 2 in that. So what is the probability of getting a card? 2. So we have 2 heart, 2 spade, 2 diamond, and 2 club. So if you, so 4 of these are there. So it means 4 divided by total number of cards, which is 52. Now you have to calculate the value, which is 4 divided by 52. So this is giving you in three decimal places, you should write 76. So if you write it down, so it means 7.6% of probability or chance that I can get 2 from any draw of card. So this is the probability. So this is classical probability because we haven't done any experiment. So this should happen. This is example. So one other example is, find the probability that a couple has 3 kids, 2 will be girls, and assuming equal chance of a boy and girl. So this is going to ask you, if a couple has 3 kids or going to have 3 kids, what is the probability that they can have 2 girls? And all of these girls or boys have equal chance that they can happen. It could be a boy or it could be a girl. So I want you to again take a pause of this video and think about whether it gonna be classical probability, observed probability, what is the favorable outcome or event in that, what is the procedure, and how you can find the probability of it. Okay, so here he discussed about probability of getting a 2 girls from 3 kids. So the experiment is, what kind of probability is it? Is this is classical probability, not observed probability, because he just said that if there is a 3 kids, the couple is going to have a 3 kids, like procedure is having kids, and if they have a 3 kids, then what is the probability, that like probability or favorable outcome, what is the event having 2 girls, and so if they have 3 kids, so 2 girls and 1 boy. So this is my favorable event. This is my event. So if you're using classical probability, so what is the number of chances that could occur in your sample space? So what could be the sample space? You need to write down the sample space. If you have, let's say, one boy or two girls, it can also happen that first time they got boy and then girl and then boy. Or it can also happen first time they got boy and then boy and then girl. Or it can happen that they get boy, all of boys. Or it could happen that they have first one girl, then boy, and then boy. Or it can happen first one is girl, then boy, and then girl. Or it can happen first one is girl, second one is girl, third one is boy. Or they can have all of these girl. Note down, these all kids are not of the same parent. Like they all are individual families, but these are all the possible outcomes that I'm going to have. If one family has three kids, then what could be the chances that they can have two girls from it? So now you have to count. We need two girls, right? So which of the event or which of the simple events has two girls in that? This one, this one has two girls, and this one has two girls. None of the other simple events has two girls. So this is how we will calculate. So it means the number of occurrences of having two girls could happen in your sample space is 3, and divided by total number of sample space, which is 8 in there. So this is how you will calculate the probability of getting two girls, which is 3 divided by 8. So this is giving you 0.375. So it means 37.5% of chance that one can have two girls from three kids. This is how. And what kind of probability it is? This is classical probability, because it hasn't performed an experiment, but we are going to find all the chances that it could happen. So this is the classical probability. So there was once a polling in stem cells. The stem cell research for the did polling for cloning, that for cloning people, that whether it's a good option or not. So they surveyed few people, like about 1,000 people, and 91 people were discussed were said that cloning is a good idea. 901 people said no, cloning is a bad idea. 20 people said has no opinion, that whether it could they were neutral, they can, okay, it might good, it might be bad. So what is the probability of randomly selecting a person who think cloning is a good idea? First of all, you need to know whether it's a performed experiment or performed procedure, or this is something that you are thinking it should happen. So again, it's a polling. They surveyed already some few people. So if they surveyed few people, it means they have done some experiment. They have the data that, okay, these people said this, these people said this, these people. So it means this experiment has already done. So what you have to do from this, you need to find the probability of those people who said cloning is good. So how many people has said cloning is good? 91 people said that cloning is a good idea. So number of people who said cloning is a good idea divided by total number of sample space, all the people. It can have who said bad, they said, it can have all those people who has no idea, it can have all those people who said this is a good idea. So these, if you add all of these, 91 plus 901 plus 220, so this will give you 1012. So then you find the probability, it will give you point in 3 decimal places. Why I'm writing it in 3 decimal places? Because you need to find the percentage, you have to find multiplied it by 100. So this is this 0.09 is the value. It means 9% people said that this is cloning is a good idea. Again, this is not a classical probability. This is a performed experiment. So this is observed probability or empirical probability. Okay, one thing I want you to know that the probability will always, always, always lie in between 0 and 1. If this is 0, if something you said the probability of getting this is 0, like, so that means it is impossible. It is not gonna happen. This is this is definite that this is not going to happen. If your probability is 1, so that means it is certain, like you are sure that it will happen. No matter what, it will happen. So this is called probability of getting 1. Or if your anything, your probability is in between. For instance, here I have shown you one of the picture, like probability of getting, like if you are tossing, if you are rolling a die, then probability of each of the faces are equally likely to happen. So if you get 1, so 1 by 6 is very small amount. So this is going to be here. So it means very less chance of getting a 1 from 6 faces for rolling a die that you will get 1. So this is unlikely that it can, but it can happen, but very unlikely because probability is less than 0.5. So that middle one is 0.5 because 0 and 1, the middle value is zero point 0.5. So if something has 0.5, it means 50% of chances it can happen or it cannot happen. Like tossing a coin, because it has two faces, head or tail, both has equally likely can happen. So both has equally chances. So 50% of chances that you can get head or 50% of chances that you can get tail in rolling, in tossing one time. So likely is something that is highly likely happen. Like you have five balls and four of these balls are blue, like maximum number of amount is blue. So how likely it can happen that if you mix it together and then you get one ball out of it and that is blue. So this is highly likely can happen because the number of balls are higher. So when you divide it by 4 by 5, for sure it will give you more chances to get, like 80% of chance you will get blue ball. So this is called probability. So probability 1 means certainly happen, it will happen, it surely happen. If probability 0, it cannot happen. So it is impossible to have it. Something in between, that means 50% of chances it can happen or not. Okay, so what is law of large numbers? Excuse me. What is law of large numbers? Why do we need it? So law of large numbers we use like for instance, if you are let's say I am going to do an experiment. Law of large numbers states that sometimes it happens that you have to do more observations, you have to do more experiments to get a favorable outcome. You are not sure that it is going to happen. For instance, if you have let's say die and you roll it one time, I am going to ask you that how, if for instance you roll a die 10 times, how likely you can get uh, or 5 times, you how likely you will get three head in that. So it's three two faces in that. So you are not so sure, like you it because all of the faces have equally chance that can happen. But if you are making less experiments, you are not so sure that what could be the probability of certain outcome that you are looking for. So if your number of outlet, but the same procedure, if I do like tossing a coin 3,000 times or 100 times, and I'm going to say, okay, can it, or like 6,000 times I'm going to toss the coin, I'm going to toss, sorry, I'm going to roll a die. So what is the probability of getting a 6 in that? So it will be 1,000 times at least, with the proportion of getting you will find the proportion of it, because each of the faces have equal chance that can happen. Because then you what you will do, if you want to get 6 in that, you will roll a die over and over and over and over and over. So then the proportionally, if you will divide the number of experiments, then it would be the same, that if you are doing your experiment 6,000 times, and for rolling a die, then then approximately you will get 1 by 6th portion, like 1,000 times you will get 6,000 sorry 6,006 faces in that. So the proportion of getting something is the same as the total number of outcomes in that. So this is what it says, that the law of large number states that as more observations are collected, the proportion of occurrences with a particular outcome. So occurrences, proportion means chances. What is the percentage that you are going to get from your number of experiments? So proportion of occurrences with a particular outcome, like event that you are looking for, that is it converges to the probability of that outcome. For example, if I am saying probability of 1 from rolling a die is 1 by 6, right? So I know that the probability of getting 1 is 1 by 6. But if I roll one time, I don't know what is the probability. It will be 1 by 6. If I roll 5 times, I don't know. It might have the probability is 40%, or like I don't know how much. But if you do your experiment thousands, like 6,000 times, so the proportion for 6,000 times, at least 1,000 times you are going to get you will get approximately you one will get 1 from 6,000 tosses, or rolling a die. So this is what all it means, that the more procedure is repeated, the closer your empirical observation or observed probability will get to the classical probability. Or classical probability is that this should happen. So will be very close. Your observed probability will be. For example, let me give you one of the example. If you are rolling a die 100 times here, let's say I'm going to roll a die first 10 times. Let's say I don't have a die right now, but let's say I draw a coin first time. Sorry, I roll a die first time. I'm getting one time. I'm getting 1 time 3, and second time I got 4. Third time again I got 3. Fourth time again, let's say I'm getting 2. Third time I don't know. Maybe I'm getting 3 again. Fourth, again, sixth time you try, you are getting fifth. And seventh time you tried, you are getting 3 again. So eighth time you are trying, so let's say you are getting 1, and then you are getting again, so let's say so these are the 10 experiments I have done. But then you say, oh, the proportion is not him. Not a single time you got 6 in that. So there you said that, okay, probability of 6 is how much? This is 1 by 6. But you are not getting proportion of that. Like, you are not getting even single time. So here probability is 0. But if you performed your experiment 100 times, then you might like this. You might like this. You can do an experiment. You might can have this kind of look like. It will look like this. Like, it will look like this. But if you do like, the more experiments you do, then you can see that the proportion it is not all equally same, because these are the extras you are going to get from your possible proportion. But if you make a proportion of each of these, then highly likely that proportion of getting a probability, it will be very close. The proportion, I'm again writing, the proportion of getting 6 is very close to, or approximately it will be probability of 6 in that, which is 1 by 6. This is our classical probability. It means the proportion of getting 6 or observed or our experiment of getting 6 from our experiment will be very close to the classical probability. This is what all it says, that the more procedure is repeated, the closer observed probability will get to classical probability. It will not be equal, but it will be very close to the classical probability. This is what all it says, law of large numbers. So here it means same thing. I'm writing I think double time. Given a large number of trials, like 1,000 times, we would expect to the observed number of heads to be close to the expected number of heads, because number of heads are equally likely to happen. So half of the chances that it can happen. So if you are doing 1,000 trials, 1,000 tosses of a coin, so you might probability very close to like 500 times or 550 times. So the proportion will be same you will get, because this is how we make predictions for the bigger things, for the stock market or for business, or like how they can invest something into something, because the because they need more trials, they need more experiments to get the few favorable outcomes they want to. This is why we need large number of trials, large number of experiments to get a favorable outcome. So this is why we need more trials. So the more problems you do, the closer you get the expected probability. Expected probability means classical probability. So which of the following event would be the most surprised by? This is my question. Exactly like three number of heads. You are getting 10 coins. So which one will be more surprising? Exactly three heads in 100 coin flips, exactly three head in 1,000 coin flips. Which will be more surprising? I want you to take a pause. Which is more surprising? How it can happen? So this is what I want you to think on. So take a pause and think on it. All right. So exactly three heads in 10 coin flips. It's highly unlikely it could happen. Might be, but it will be but it can no it can happen. Like three heads, you might there is a possibility, because the proportion you are getting the same. Three head in 100 coin flips, okay, you might, yeah, it's in medium, yeah, it might happen but might not. But first one might, you're very sure that okay, it can happen. But surprisingly, you can see the 1,000 number of trials, like you have done 1,000 number of flips, 1,000 number of trials you have done, and you are getting exactly three heads. Something is wrong, something is fishy. This is what your intuition says. Something is going to wrong, that I am doing my trials like thousands and thousands of times, and I am getting just three times three heads. So something is wrong. So it means the surprising thing is this one. So it means why you thought this is surprising. It's surprising for you because the number of trials are a lot, and you are not getting three in more than three. You're not getting head more than three times. How can it can happen? So this is why, because you think, okay, if your number of trials is more, number of chances are more that you can get. This is why we need law of large numbers. Okay, so the next thing is complement. Complement means is something excluded, right? So you don't count it. Complement means that you are excluding that things. So this is what complement comes from. Complement of an event A is a set of outcomes not contained in A, or is a set of all outcomes when event A does not occur. Like I want to say, let's say I have these cards. I have these deck of cards, and I want to exclude all hearts. What is the complement of heart in all of these decks? So in deck of cards. So what you will do, you will take out all the 13 cards, 13 heart cards from that. So then you will left just 13 spades, 13 diamonds, and 13 clubs, but no heart will be there. So it means uh, the set is 52, and if you want to exclude the set of like this event heart, I want to take out. So 13 you will exclude from 52, and the rest of the set, which includes heart, sorry, not heart, club and club, diamond, and spade. That these three will be left. So it means something that you are taking out from the set. So that is called complement of the heart. So it means complement of any event A, your favorable outcome, if you are taking this out. So this is denoted by A bar. Complement, it can be represented by A. But X bar doesn't mean that you are taking the event out, because that X bar you are using for mean, not for, don't confuse that thing with this thing. Mean, sample mean you are representing by X bar. That doesn't mean complement. That is not probability. That we are not going to consider in this section. That complement, that thing mean is different, and this thing is different. If you are taking complement of a set, that is also denoted by this, but usually you will not see the complement of a set with X. X you are not going to, because X is a variable. So events we are going to represent it by A, B, C something, but not most X a variable something. So this is the, if you are taking the complement of an event A, so this is denoted by A bar. Okay, so the probability, the next key thing is probability of an event plus the probability of complement of that set of that is going to happen. If you combine them, this is going to the one. The total chance of getting one, like if I'm saying like head or tail, head or tail, they are equally likely to happen. This has chance 50%, this has chance 50% that you are, and head is complement of tail. This is tail, and flipping a coin, and tail is complement of head. So both has equal chances. So it means probability of head plus probability of getting complement of head, which is tail. This is equal to 1, because this is 0.5 and this is 0.5. So 0.5 and 0.5, this is 1. So this is how we find the probability of a complement of an event. So here is an example. What is the complement of rolling a 5 on a die? Or what else could happen of rolling a die when that does not make a 5? So it means it is asking you, the dice has 6 sides, 1, 2, 3, 4, 5, and 6. All of these faces have equal chances of happening. So you know, you have to find this. He is asking you the probability of not getting a 5. So complement of rolling a 5. So not getting a 5. So how you will find it? What we have a formula that probability of A plus probability of complement of A is equal to 1. So probability of 5 complement equals to 1 minus probability of 5. So probability of 5 is 1, because these are equally likely to happen, and 5 is occurring only one time in our dice. So this is 1 by 6. So then you can find it out. So this is 5 by 6. It means probability of complement of 5 is 5 by 6. So this is the probability of complement of 5. Next is probability of, what is the probability of even numbers in rolling a die, and probability, so the probability of even numbers, if you have to find, it means the complement of even is odd numbers. 1, 3, and 6, sorry, 1, 3, and 5, these are odd numbers, and 2, 4, 6 are the even numbers. So what is the probability of getting even numbers in rolling a die? So I want you to think on it. Probability of even numbers, which is 2, 4, and 6. This is what you have to find out. So what you have to do, you can do two things. Either you can take the complement, or you can take the probability of each of these. So this is how you have to find out. Okay, so I want you to try it on. If it doesn't work, then I can do it for you. So let's try it first. Okay, the next question is, what is the probability, if your probability of event A is 0.64, what is the probability of getting a complement? You know the rule. Again, don't forget the formula. Probability of A plus probability of complement of A equals to 1. So probability of A is given to you. So how you can find probability of complement of A? This is 1 minus probability of A, because probability of A plus probability of complement of A gives you 1. So you have to calculate 1 minus 0.64. This is giving you the value minus 0.64. This is 0.36. Again, if probability of complement of A, then what is the probability of A? Again, you are using the formula, which is probability of A plus probability of A complement. I want you to work on it. So you have this thing. Because 1 plus 1 probability of A, this is giving you 1. So you have to subtract probability of A complement. So if probability of A is 0, what is the probability of A complement? So it means if A is not going to happen, then for sure probability of A complement is going to happen. So like head or tail, if head is not going to happen, then for certainly tail is going to happen. So it means then what? Because again, I'm using the rule. If by rule you will say probability of A plus probability of A complement, this is equal to 1. If this is 0, then probability of A complement is 1. So this means probability of A complement is 1. This is certain. If something is not going to happen, then complement is certainly going to happen. Okay, so the next thing is compound event. Compound event we use for the event, an event which joins two or more simple events. Like we want two things are going to happen at the same time. So that is called compound events. It could be joint or it could be disjoint. What is the probability of rolling a 1 or 5 or one or the other or both? It means in a single trial, you are going to look for probability of rolling 1 or 5 or both can happen. So then we use uh, compound events, like both things are going to happen single time. So so for instance, in Vegas they do some gambling. So in gambling there is a game called crap. So what do they do? The rule is, if you're going to get they roll two dice at the same time. So if you're going to get 7 or 11, then you're going to win. So for instance, uh, I'm going to roll one die at a time. I'm going 6 in that. So what other things I should get in a second die that I could win for getting 7 or 11? I might need one, or I want to get 5 in that. So that can make me win uh, to win that game. So this is why I either I want this or this. Any of these things can happen, then I can win the game. So this is why probability. This is where we use compound events. That what is the probability of getting one, probability of getting 1 or 5, or one or other or both can happen at the same time. So this is why we need probability of getting A or B. So we are writing in English. We are writing probability of A or B. I'm not going and, I'm using or B. So probability, what does it mean? That probability of event A occurring or B occurring or both occurring in the same trial, in a single trial. So that is, for instance, probability of blonde and female. Like if someone has a kid who is a female, and what is the chance that it could be having a kid at the same time? You cannot get two times. You can have a baby and it cannot happen that you are going to get two kids. You cannot cut it into half until he's crazy. So probability of getting a female or blunt, like it can happen at the same time. It can happen she's a baby girl, or she has a blonde hair, right? Both can happen at the same time. So these are not mutually exclusive. Mutually exclusive events that cannot happen at the same time. So those are mutually exclusive events, disjoint events. But the events that are not disjoints, that are compound events, it can happen at the same time. So that means that is not mutually exclusive, blonde and female at the same time. So what is the probability of that? This is what it says. So, so if we talk about the mutually exclusive events are those events that cannot happen at the same time. For instance, rolling a one, if I'm rolling a die one, I want to get either odd or even. It cannot happen at the same time. You cannot say it has to be one and it has to be even as well. No. If you are rolling one time in a single trial, you want to get both of these things these both things cannot happen at the same time. Similarly, if you're rolling a die, but in this case, this is mutually exclusive. Why? Because rolling a 2 or 4, if the probability of getting A is rolling a 2 or 4, both of these can, one of these, but one of these can happen. Second event is it has to be prime. But if you are getting 2, and so 2 is a prime number, so it means both can happen at the same time. So this is mutually exclusive. This is not mutually exclusive. This is not mutually exclusive, because both can happen at the same time, because 2 is a prime number. It can happen, you can get 2, and 2 is also a prime number, just like female has could have blonde hair, and she is a female. So here is an experiment. This is the table for a jury. There was a jury who is going to decide that a person is a victim, is finding it guilty or not guilty. So four of things can happen in that. One thing is a person who did not do anything, and they found that he is a guilty. It's the worst case, that he said, for instance, let's say a person got the ticket, but he is not was speeding up, over speeding. So that is really, it can happen. That these things we don't want. So it means this fact is false, and they proved it positive, guilty positive, and these things they don't want it to be happen. This is the false statement, like he didn't do anything and he found guilty. 72 people found did it and they guilty. This is true fact. Fact is true, and they find it positive. He is guilty. They are guilty. Or if they surveyed 85 people, they did not do anything and they found non-guilty. So this is a true fact. They did not do anything. This is true, and they found non-guilty. Statement is negative. So one thing can happen, they did it, something they did wrong, and they found non-guilty. That some person feel very happy, okay, I did it, but I haven't been caught. So hey, yeah, but something like this. So, but did it, but they did not find guilty. So it means the fact is false, because they did it, but they didn't found non-guilty. So this is, the fact is false, the something is going to happen wrong here. So, and they found negative result for them. So this is what this chart means. And now I'm going to find that how many people are guilty and did it. Like they are guilty and they found that this is that they did something wrong. How many people are there? Like I want to find the probability of guilty or did it. So how many people are guilty? If you see how many people are guilty, so this rows is telling you how many people are guilty, right? So guilty people are 11 plus 72, right? And or did it. So how many people did it? So this is the column is telling you that how many people are did it. So it means plus 72 plus 9. But there is a reason I'm telling you, giving you this example. I will tell you in a minute. But if you count, okay, these are the people that if you all together, they are guilty. If you find them all together, they did it. But if we count them together, like they are guilty and did it, so we are overestimating, right? Because this 72 is repeating. If we will include this 72 again, then it will increase the number of sample space. We never surveyed more than that people. So we have to exclude one 72 because we are double counting it. We don't want to count it again, who people who are guilty and also they did it. This is why we don't need it. So what you will do, um, you have to find the probability of getting guilty or did it. What you will do, 11 probability of people and plus, sorry, plus 72 and plus 9 and did it. So these are the people who are guilty and did it. So the both of these are there. So how many number of people are there? So this is um, so this is 92 number of people are guilty and they both are in there. So this is the probability of getting no, sorry, we are finding the probability. We have to divide it by overall number of sample space. So we have to find the sample space, which is 11 plus 52 plus 85 plus 9. So divided by total number of sample space, which is what? 85. This is going to 177, right? So this will give you the probability of people who are guilty or did it. So if you divide it, 92 divided by 177. So this is giving you 3 decimal places. I'm going to write 0.519. So this means 51.9% of people have the probability that they are guilty or did it. The reason I'm giving you this example, because here is the general rule of addition for probability of getting, because here you are doing the same thing here. Probability of people who are guilty, right? These are the people who are guilty, and the probability of people who are guilty, and these are the people, and 72 plus 9 people did it, right? But here we are excluding the double count, right? Because we are adding all of these, combining all of these probabilities together, but we are excluding the double count. Like the double count means we are excluding the people who bo- are who are both guilty and did it. Like they are in all together. We are deleting this over counting number. Did you get my point that 11 plus 72 people are guilty and 72 plus 9 people did it? But if you are writing it both all together, then you are overestimating the value, increasing the value more than a sample space. So this is why we don't need it. What you will have to do, you will exclude the counting, over counting. You have to exclude the over counting. Double count you have to exclude. So because 72 plus 72, this is the double count. So this is why we need probability. The probability of A, the probability of people who are guilty, plus probability of people who are who did it, and we are excluding the probability of double counting, like the both who are guilty and uh, did it. So this is why this is how the addition rule counts probability of getting A or B. So this is the rule that if you are finding the probability of A or B, then this is probability of A, probability of B, and you will exclude the double counting rule, which is existing in both of the items who did it and also guilty. So you have to exclude it. So this is the formula. If you're writing in mathematical form, so this is the way you will write it. Probability of A union B, A or B, A union B, combining them together. Probability of A plus probability of B minus the probability of a set that are occurring in both sets, A and B, intersection of A and B. So this is the probability rule of addition for the probability. So now here we are two cases. If you have mutually exclusive events, we discussed two events. You can have mutually exclusive events, or you can have compound events, not mutually exclusive events. If you have disjoint events or mutually exclusive events, that means these two cannot happen. These events cannot happen at the same time. Like probability of getting probability of getting one or probability of getting even number from a die, it cannot happen at the same time. Then that in that case, the intersection of all of these items is zero. So if your probability, these are disjoint events, cannot happen at the same time, it means their intersection, probability of A intersection B will be zero. So if you substitute this thing in addition rule, probability of A union B, so this will be zero in mutually exclusive, in mutually exclusive, right? So this is why we, if mutually exclusive events, we will use this formula. If these are not mutually exclusive, that can happen at both at the same time, then we will use this formula, probability of A union B plus probability of A plus probability of B, and minus the, like deleting the double count, which is probability of A intersection B. This is how it happens. Now we can define it into Venn diagram. Venn diagram is a graphical representations of for any probability of an event in a curves, in a rectangular enclosed box. You can represent it. So in this case, if you count the probability of A, so I'm coloring it like this way. Let me color it, which is this one. So this is probability of A. If you found, so this will exist into it. This is probability of A. This is my A set, probability of A exist into it. This is um, so this will be probability of A. If I need to find what is probability of B, then if you have to find probability of B, so what will happen? So probability of B is this one. This is all the things it will exist into it. Probability of B. This is my probability of B. So this lies into it, right? So if you find probability of B, so this is my probability of B in this set, you can write. And if you want to find the intersection, they are over where the section where they're overlapping with each other, right? I can, if it is overlapping, so this is the case, the both green and white both will exist into it. Like this is the section where my probability of A intersection B can occur. So if you just like defining it in a set, so this is A, this is B, you don't need to write probability. This is, what's that? This is B, this is set B. And if you define this is my A intersection B in there. So if you find, so this is how we define that this is the A section will exist into it, B section into, if you are disjoint event, for instance, if you have disjoint events, then what kind look like, this is A and this is B. If this is disjoint, this is A, this is B for disjoint events. So you can define it. They're like no, there is no intersection B. They are not overlapping with each other. So these are some rules that I have defined. If you are taking A union B, like bigger set, so it must be greater than equal to probability of A. So probability, if you're defining A union B, you can see from here that it also contains a part of A, also contains a part of B, and also the intersection of it. So probability of A union B will be greater than or equal to probability of A, and it will also be greater or equal to probability of B, and probability of A is also greater than equal to probability of A intersection B, because intersection is a very small part, and it definitely be less than the A circle. This is why probability of A will be greater than or equal to, unless it all the part will be existing into it. So probability of A intersection B, and probability of B is greater than equal to probability of A intersection B. So these are the rules that you have to, using these that I have, these are the rules that I have defined here for you, or you need to just um, keep it in your mind that how these rules works. Based on these rules, I want you to look at these example, that is there something wrong with that? Um, there is something wrong in it. So these are the things, for instance, using that rule, is it a, because probability of A union B should be the bigger set than probability of A or probability of A intersection B. But this is bigger. So probability of A intersection B, okay, this is largest number, but probability of A intersection B has to be smaller than probability of A, or it has to be equal than probability of B, because probability of A intersection B less than or equal to probability of A. But here probability of A intersection B is 0.5, and which is less than equal to probability of A, which is 0.3. So this cannot happen. So this cannot happen. So this is why this is the wrong statement. Similarly, I want you to think on the second example, this one, by using the rules. Is there something wrong with that? And if it is, then what is the problem? So here are a few examples for you to find the probability. I want you to look at their procedure, which probability it is, and what are their probabilities. Like this is classical probability, empirical probability. Is it mutual? Is it disjoint? If it is disjoint, what could be the probabilities? Probability of heart and spade. I can solve one for you. So probability of getting heart and spade as a single in the same trial, in a single trial. Can it happen? So probability of heart and a spade, or a spade. So what is spade look like? So spade will be like, you make it like this, right? So this is spade. So what is, so you know the addition rule. Addition rule is probability of this event plus the probability of spade, which look like this, and minus the probability of double count, where the intersection can occur. But you know that in deck of cards, these things cannot happen at the same time. So this means these are mutually exclusive events. So if this is mutually exclusive events, this is equal to 0. So what is the probability of getting heart? 13 number of cards are in there. Divided by total number of cards are 52, plus probability of getting a spade card, which is 13 in there, and these are also 13, and you are dividing it by 52. So what will be the probability? 26 by 52. So this is giving you, I think 52%, 50%. So this is 0.5. So it means 50% of chances that these two can happen in a single trial, like one time you are trying one experiment and you want this, the probability of getting both of these. So then we use addition rule. Similarly, this probability of getting blunt and female, let's say probability of blunt is 0.18, and probability of female you are having zero 0.6. So what is the probability of getting blunt and female at the same time or in the single trial? So again, you have to use one thing I haven't mentioned, the probability of getting both and female. This is 0.12. So I want you to find the probability of blunt and or female. So how you could find it? You will use the probability addition rule of probability, blunt plus probability of female minus the double count, blunt intersection F. So this is what I want you to calculate. Again, I'm leaving it on you. You have to calculate the probability of getting diamond and K. King, you should remember that it has to be, you need to use probability of getting king, sorry, diamond or K in a single trial. So what is the probability? You need to use this formula plus probability of king minus the double count, which is intersection of K. So this is how you have to calculate. And we know that king uh, is this king already in diamond also. So that is existing only one time. That a card can be, let me show you, a card can be like, this is the card that is king, that is king or diamond as well. So it means this card, this is a one card only in 52 cards, which lies in the intersection of diamond and king. So 1 by 52 is the probability of getting diamond and king. So and probability of diamond, 13 overall diamonds are there, and so 13 by 52. Probability of king, we have 4 king overall in the cards, which is for 1 king for diamond, 1 king for spade, 1 king for heart, and 1 king for club. So 4 number of kings we are having. So for this thing is 4 by 13. So this is the last slide, probability of complementary events. What are the probability of complementary events? Like we know that if you have two um, events, one is event and one is the complement. If you want to take their addition, then by using addition of probability, what will be what will be its probability? Probability of A plus probability of its complement minus the probability of the event and its complement. So we know that complement of a set and a complement of that event cannot happen at the same time. So this will be 0 in that. So this means probability of A or A complement is equal to probability of A plus probability of A complement. And we know that if you add them together, probability of event plus probability of complement of an event, this is equal to 1. So from here, we can easily see that if you want to calculate probability of A, you can find it out 1 minus probability of A complement. If you want to find the probability of complement of A, event A, then you can find out 1 minus probability of A. So this is the probability of complementary events. So hope um, everything is done now. So I want you to do some exercises. I will give you one exercise that you can perform. Last time we discussed few things on Chebyshev's and empirical rule, and I want you to do some questions on that. You might be asked for the interval or percentage, or also you can be asked for finding the standard deviation and the mean, and the rest of the things will be given to you. So I will give you a few questions on that to perform on it. So if you have some questions, you can ask me. Um, so see you next week.